All right, welcome everybody. Today we are going to be talking about types of bonds. What you're going to need is your journal open to the next blank page, and then you're going to draw some things with me. It'll be kind of like poster notes, but I'm a video instead of in real life. So you're going to draw what I draw on the screen here, and I'll talk you through some things. If you need to pause me at all or rewind me if I was going too fast, feel free. I won't mind, I promise. So I'll give you a second to open your journal, and then we can get started. All right, so to start with, you are going to draw some things on your paper. So you're going to make your paper into 3 separate sections, kind of like I am right here. So you'll have 3 separate sections, here, here, and here. I'll get rid of those. Okay. In the top left box, you are going to title it Ionic. And that's spelled I-O-N-I-C. Man, my handwriting's bad on a tablet. That's okay. Ionic. Okay. The next box, or the next section over here, you are going to title Covalent. Let's see if I can do any better at this one. Covalent. Covalent. Okay. And on the bottom here, you are going to title it Metallic. And I'm just going to put it down here in the corner so that it doesn't get in the way of me writing anything. So I'm just going to write down here Metallic. Metallic. I'll give that an underline. Perfect. Okay, so before we get talking about this nitty-gritty and each of these kind of bonds, I want to talk about why they're important. Okay, so ionic, covalent, and metallic are all ways atoms can bond. Remember, the only reason atoms really do anything is because they want to be stable. They want that full octet. So remember, in a ring, this is my atom. Its octet is its outer shell, and it always wants 8. And very few naturally have 8. So what it does is it has tricks in order to get that full 8. Sometimes it steals, sometimes it gives away, and we're going to talk about how it can complete its octet. There's really only 3 ways it does that in the real world. Let me zoom back up here. Okay. The first is by ionically bonding with someone. Or when I say someone, I mean another atom. So I am going to choose a different color here. I'll use red, because why not? So first, let's talk about the goal of ionic bonding. Okay, the goal of ionic bonding is to fill your octet and become stable. So if someone ionically bonds, their goal is to fill their octet to become stable. So I'm going to write goal fill octet and become stable. Stable. That's a T. Fill their octet and become stable. Okay. And the elements, the kind of elements that ionically bond are metals and nonmetals. So remember, metals are found at the left-hand side of the periodic table, and nonmetals are excuse me, found at the right-hand side of the periodic table. So we are going to, you're going to write, we'll do orange. Okay. We're going to say that this happens, ionic bonds happen between metals and non-metals. Metals and non-metals. Metals tend to become positive ions because they're usually just a couple over an octet, so they'd rather give them away. And non-metals generally form negative ions or anions because they're usually just really close to filling that octet, and so they gain them from somewhere. Okay, so the one thing I want you to notice about this is that these two atoms, so metals and nonmetals, have a large electronegativity difference. And what we're talking about electronegativity is that electronegativity is that greed for atoms. So remember, nonmetals are found way over there on the periodic table, on the right-hand side, where there's lots of protons and there's not very many rings. And so they have their electrons very close and tightly held. And not only do they hold their own electrons tightly, but they hold other atoms' electrons tightly. So they're greedy for electrons. Metals, on the other hand, they're like, take my electrons, I don't care. I don't want them, right? Because they want to get rid of their electrons anyways, because they're really close being full octet if they just lose one or two electrons. And so what I want to point out for the ionic bonds is that these atoms have a large electronegativity difference. I want to use green for this one. Okay. So I'm going to say in an ionic bond, the atoms have a large electronegativity difference. So large electronegativity difference. Okay, and En is just my abbreviation for electronegativity, how greedy an atom is for electrons. Okay, so what happens when one atom gets together, or excuse me, one atom that's super greedy gets together with an atom that's like, I don't really care. What happens is that this atom that really wants those electrons, it's really close to filling its octet, and this one that wants to give it away to fill the octet, they're going to transfer, or this one's going to give its electrons to the non-metal, or the one that wants it really bad. I'll change the color one more time. So what happens, in other words, is electrons are transferred. Okay, so I'm going to say electrons are transferred. Sorry, spelling is really bad on this. Transferred, and that's just an academic term for given away. Okay, so electrons are given away to the one that wants them more badly. And an example of this is sodium chloride. So Na is sodium, and it has just one valence electron. So I'm going to draw one dot at the top. There we go. And if it gets together with chlorine, which is Cl, and it has 7 valence electrons because it is in the 7th column of the periodic table, what's going to happen is sodium that's like, I need to get rid of it, is going to give it to chlorine. And what's going to happen is it's going to be, I'll draw it down here, Na positive, I'll put some brackets around it, and it's going to be bonded to Cl minus. Okay, and I'll draw some dots around here to show that it has its full octet, or it gained one to get its full octet. Oh, there we go. It's a minus. These are valence electrons. Okay, so we've got a positive ion and a negative ion. And what we learned when we were talking about Coulombic attraction, we talked about this extensively, is that opposites will attract. So once sodium gives its electron to chlorine, what happens is they've got a charge, a positive charge and a negative charge. So they will literally stick together like magnets. And so what holds this bond together, what holds an ionic bond, is just simply opposites attract. And so we're going to write that. Not that. We're going to write one last thing here, and we're going to say we'll use pink. We're going to say atoms stick together. Atoms stick together. Oh man, I'm really running out of room. Because I'm totally out of room. You're going to finish that for me. You're going to say atoms stick together because opposites attract. Just like magnets, the opposite sides attract. Sodium is positive and chlorine is negative. So opposites will attract and stick together, or bond in this case. Okay. So go ahead and say finish that. Hopefully you have a little more room than I do. Say atoms stick together because opposites attract. Okay. And so that's an ionic bond, right? So there's a transfer of electrons and then they stick together. Next, we're going to talk about covalent bonds. And something happens just a little bit differently. But what is the same about covalent bonds and ionic bonds is they have the same goal. So the bond for ionic and covalent bonds is always to fill an octet and become stable. They just do it in a slightly different way. So we're going to say the goal for covalent bonds, is to fill their octet and become stable. Become stable. That is an S. I super apologize. Not my handwriting so bad on this. But I will try to say everything I'm writing. Okay, so the goal here is to fill the octet of both atoms to become stable in covalent bonds as well. But the way they do it is slightly different. So in order to talk about how they do it, we got to talk about what two atoms covalently bond. So covalent bonds always happen between two non-metals. So I'm going to use orange again. And I'm going to say covalent bonds happen between two non-metals. Okay. And remember, non-metals are those ones that are on the far right side of the periodic table and are really greedy for electrons because they have a lot of protons in their row. A lot of protons for what row they're in, and they usually have fewer rings. So the electrons are really close to the nucleus. They're really attracted and tightly held. So one thing about two nonmetals is that they are both have high electronegativity. So when two nonmetals get together, they're both really greedy for electrons. And that's going to dictate what they do to become stable or what they do to bond. So I'll say green again. So we're going to say both have, that is too light. I'm going to use a darker green. That's a little better. So both have high electronegativity. Both atoms have high electronegativity. High En. Remember, En is just for electronegativity, how greedy they are for electrons. So they're both really greedy for electrons. So what happens when two elements that are greedy for electrons get together is they're like, give me your atoms, or excuse me, give me your electrons. And this one's like, no, give me your electrons. And so what happens is they end up pulling on each other's electrons, and they almost are in tug of war with each other's electrons. And what ends up happening, or what we see because of that, is they both hold on to those electrons, and so they share electrons. And so those electrons are kind of counted as this guy's octet. They're also kind of counted as this guy's octet. So they've shared electrons to make up for the ones they're missing. Okay, so I'll give an example of that. I want to switch to blue really quick though, so that we can color code this real nice. So we're going to say here electrons are shared. Electrons are shared. And an example of this is I'm going to draw a chlorine atom with its 7 valence electrons. I'd like you to draw that as well. And another chlorine atom also with 7 valence electrons. 2 and 2. Okay, so they're both really close to filling that octet, right? And so if they get together, what's going to happen is they are going to share these 2 electrons in between them. So they both count as each other's octet. And I'll show a picture of that. So what happens is we're going to have this chlorine, and we're going to have this chlorine, and I'm going to draw this guy's original 7 valence electrons, and I'm going to draw this chlorine's original 7 valence electrons. And so what you can see here in the middle is we've got 2 electrons in between them, and those are their shared electrons. So those electrons count as this chlorine's octet, but it also counts as this chlorine's octet. So they're both have a full octet, they just go about it slightly differently. They're sharing instead of being transferred, transferred electrons. Okay, and so they stick together, or they bond for slightly different reasons. In ionic, they bonded because opposites attract. However, in covalent bonds, they stick together because they both have a hold on those electrons, and neither are letting go. So I'm going to switch to pink again, and we're going to say, pink, hot pink. The atoms stick together because they both hold on to the electrons. Neither wants to let go. So I'm going to say here they bond or stick together. Atoms stick together. I'll abbreviate because, just because I'm out of room. Because both hold on to electrons. Okay, neither one of those, remember, they're super greedy. Neither one are gonna let go. So they're gonna be like, no, they're mine. No, they're mine. So they end up both holding on to them. They end up holding on to each other in the process. Okay, so that's covalent bonding. Again, the goal is the same, but they go about filling that octet in a slightly different way. Okay, the last one we're going to talk about, and there's really only 3 ways atoms go about filling their octet, 3 strategies: ionic, covalent, and the last is metallic. So metallic bonds, they, surprise, surprise, have the exact same goal as covalent ionic. So the goal for metallic bonds is the exact same. The goal, when there's a metallic bond involved, is to fill octets and become stable. So the goal is to fill octet and become stable. Awesome. Okay. However, instead of being between metals and nonmetals or two nonmetals, metallic bonds happen between, as the name implies, two metals, two atoms that have a pretty loosey-goosey hold on their electrons already. Okay, so we're going to talk about orange. No. Okay, so metallic bonds happen between two, we'll say only between metals, period. Okay, so metallic bonds only happen between metals that have a low electronegativity and they're pretty loosey-goosey hold. And so we're going to write that in green because that matters as far as what they do. If they have a pretty loosey-goosey hold on them, then neither one's going to steal atoms, or excuse me, steal electrons, because they don't want them very bad. So we're going to say metal atoms don't know why I capitalized that. Metal atoms have low electronegativity. Okay, so they're just like, hey, take my electrons, I don't want it. And remember, that's because metals typically have a lot of rings, so their electrons are really far away. And metals typically have fewer protons for their row, and so they don't have a very strong hold on their electrons for many reasons. Also, that comes into play in that most metals want to get rid of an electron to fill their octet, and that's one of the reasons why. Okay, so what happens when two metals get together? They still want to fill their octet by getting rid of their electrons. So when they get together, they just let them go. What happens is they let their electrons go, and they float around in what's known as a sea of electrons. So it's like a bunch of electrons that are just like floating in between these atoms. And so we're going to draw a picture of that really quick. I'll use blue because I want to keep it color coded. So an example or a picture of, let's use, I don't know, let's use magnesium. No, let's use sodium. I'm going to use sodium. So sodium is Na, okay, and it has one valence electron. So when it gets together with another sodium atom, or let's say multiple sodium atoms, we'll just get a bunch of them in here. Na, okay. What happens is they let their electrons go. And so I'm going to say that this electron came from this one, and this electron's floating, and this one is floating away. Okay, and once they've been let go, they're free to move around. Okay, so all of those electrons have let go of their one valence electron, so we've got 5 valence electrons just floating around. And this is known as a sea of electrons. So we're going to say electrons are released into a sea of electrons. We'll say electrons. Let me scoot it up just a little bit so I have enough room. Electrons are released into a sea. Electrons released into, sorry, it's small, a sea, like an ocean, of electrons, period. Okay, and they're just floating around. And then so the reason these guys stick together is because as soon as those sodium atoms release their electrons, they are now positive ions, or positive sodium cations. So I'll put a little plus on all of these sodiums to show that they're now positive. They've lost a negative charge. When you lose a negative, you're now positive. So sodium is now positive, and the reason these sodium atoms stick together is because of they still hold on to, because opposites attract. We've got positive sodium ions and negative electrons. They kind of attract a little bit. Okay, and so when they attract, and even though they're moving around, they kind of stick together because this sodium atom is sticking slightly to this electron. This one is too. There's kind of like a web, of attraction here. So the sodium and the electrons kind of stick together, and they're kind of moving in that sea of electron. And that's one of the reasons why metals are very malleable. It's because the electrons are free to move around, and therefore the sodium ions, or the positive ions, are free to move around as well. So we are going to add one last thing. Pink. There we go. And we're going to say atoms stick together, again, just like ionics, because opposites attract. The negative electrons and the positive cations attract each other slightly, so they stick together. So we'll say atoms stick together, or bond in metallic bonding, stick together because opposites attract. Phew. Okay. Hopefully yours is just slightly neater than mine. It's okay if you didn't color code it. That's totally fine. I just did it to show similarities and differences between the things we were talking about. So what you're going to do, and when I'm back, well, I'll answer more questions about this. We'll do a little practice with this. But for right now, I want to check your learning, how well you're doing on this subject. So on this OneNote page, you are going to find a forms quiz. And I want you to take that quiz to the best of your ability. There's a couple short answers, a couple multiple choice, a couple choose the 3 best answers or 2 best answers. And you're going to take that so I can check your understanding, how well you're doing on this. Take a thermometer temperature of how well people are doing. Okay, so I am going to sign off. I'll let you take that quiz, and excellent job.